Hello, welcome back. In this video, we'll discuss the structure, working principle, and characteristics of a solar cell. A solar cell is a PN junction that can generate electrical power when illuminated with sunlight. It is essentially a PN junction, and it can generate electrical power when illuminated with sunlight. Since this is a solar cell, it operates in the photovoltaic mode. What is photovoltaic mode? If the diode is left on open circuit, then you call it as photovoltaic mode. In photovoltaic mode, an externally measurable voltage appears between the P and N regions. Now we shall see the structure. You will have a metal contact. On the metal film, we have a lightly doped P-type semiconductor. Over the P-type semiconductor, we have a thin layer of heavily doped N-type semiconductor. Over that, we have a contact. Over the contact, we have the anti-reflection coating. Over the anti-reflecting coating, we have a glass cover to shield the structure from the environment. We have here anti-reflecting coating because light should not be reflected back. It should be absorbed by the junction diode. Since we have a heavily doped N-type layer and a lightly doped P-type layer, for this kind of a PN junction, a large portion of the depletion layer will spread into the P-type region. When light enters into the junction, electron and hole pairs are generated, and the electrons they move towards the N-type semiconductor, and the holes they move towards the P-type semiconductors, and they will be separated because we have the barrier potential and we have the electric field established by the immobile ions across the junction. The movement of electrons and holes across the junction into the N-type and P-type semiconductor regions will produce accumulation of charges on the two sides of the junction, and they produce a potential difference called the photo EMF. Photo EMF is there because the created charge carriers they are separated due to the electric field established by the immobile ions. As a consequence, these electrons and holes they will be accumulated across the junction. Due to the accumulation of charges, we have an EMF which is called as photo EMF. Now we shall see the IV characteristics. If the external circuit is short circuit, or when there is no load applied across the junction, then only the current is due to the generated electron hole pair by the incident light. This current we call as photocurrent and we represent with IPH. If the junction is short circuit and when light falls on the junction, we have only current in the junction due to the generated electron hole pairs. This current is called as photocurrent. Since this current is present in a short circuited junction, we also call it as short circuit current. Short circuit current is represented with NISC. The photocurrent is related to the intensity of the light incident on the junction. IPH is proportional to IOP, that is the optical power. We write IPH is equal to some constant K times IOP, that is the optical power. K is a constant that represents the efficiency of the diode. That depends essentially on the structure of the diode. When a load R is connected, it develops a voltage. This voltage opposes the built-in potential and reduces the barrier for carrier injection across the junction. And this is similar to a PN junction in forward bias. When the external bias causes injection of minority carriers and that increases the current, this forward bias current opposes the photocurrent generated within the device due to the solar radiation. This is because IPH is generated, that is the photocurrent is generated due to electrons going to the N side and holes going to the P side due to the electric field within the device. That is the drift current. While the forward bias current is due to the diffusion current caused by the injection of minority carriers. As a result, we'll have the net current in the circuit I is equal to minus IPH plus ID, where ID is the diffusion current. In this video, we have seen what a solar cell is. We have said a solar cell is a PN junction that can generate electrical power when illuminated with sunlight. We have said that the solar cell operates in the photovoltaic mode, gives an externally measurable voltage that appears between the P and N regions. We have seen the structure. The structure consists of a metal film over which we have a lightly doped P-type semiconductor, over which we have a thin, heavily doped N-type semiconductor. Above the N-type semiconductor, we have a contact. Above the contact, we have the anti-reflection coating. Above that, we have the glass cover. The glass cover protects the structure from the environment. Anti-reflection coating stops light being reflected from the structure. We have a current in the circuit, and this is the load. While the solar cell is in open circuit, if you have light shining on the solar cell, then from the junction, we have electron and hole pairs generated. These generated electrons and hole pairs, they get accumulated near the junction. We have seen the IV characteristics. We have said that if the junction is short circuit, only the current in the junction is due to the generated electron hole pairs. We call the current as photocurrent, and the produced EMF is called as photo EMF. The photocurrent is represented with IPH. The photocurrent is related to the incident optical intensity. We can write as IPH is equal to KIOP, where K is a constant that is similar to efficiency of the structure or the diode. If you have a load resistance R that develops a voltage across the junction, this voltage opposes the built-in potential and reduces the barrier for carrier injection to take place across the junction. And this is similar to a PN junction in forward bias. So the net current I is equal to minus IPH plus ID, where ID is the diffusion current. Thank you.